Projectile motion occurs when an object is subject to no forces other than gravity. Any object that you throw or launch is a projectile as soon as you let it go, and it remains a projectile until it hits the ground. For rockets, the rocket becomes a projectile the moment it runs out of fuel and the thrust force goes to zero. Projectiles generally experience curvilinear motion. They follow a parabolic or two-dimensional path of motion. However, if they're thrown straight up, then the path of motion is rectilinear. Although the wind resistance acts on an object in Earth's atmosphere, we will assume it is negligible for our purposes. Think about these two balls. Both are projectiles since they're subject to gravity only. What is the difference between them? The horizontal lines indicate that they're falling at the same rate in the vertical direction, but the yellow ball is moving to the right at a constant velocity. So the only difference between them is that the yellow ball had an initial speed in the horizontal direction. Notice that the horizontal velocity acts independently of the vertical motion. Its vertical motion is the same as that of the red ball. Notice also that both balls are accelerating in the vertical direction, but neither is accelerating in the horizontal direction. The vertical lines are equidistant. This suggests that the velocity in the horizontal direction is constant. And when velocity is constant, that means that acceleration is zero. By convention, the y-axis is aligned with the vertical direction and the x-axis is directed along the horizon. Projectile motion is characterized by constant acceleration g in the negative ey direction and zero acceleration in the ex direction. Note that g is 9.81 meters per second squared or 32.2 feet per second squared. We will use these values a lot. Since the accelerations in both the ex and ey directions are constant, we can use the equations of rectilinear motion with constant acceleration to analyze projectile motion. But this is typically two-dimensional motion, therefore the equations are typically resolved into x and y components. We will work in each direction independently. We can even derive special forms of the kinematic equations for each direction, and we'll do that now. As I said before, by convention, the x direction is along the horizon and acceleration in this direction is zero. If we plug zero into the kinematic equations for constant acceleration shown on the right, we can obtain equations that apply specifically to projectile motion in the x direction. Starting with equation 4, rewrite the equation for the x direction only, then set acceleration equal to zero. We find that velocity is constant and equal to the initial horizontal velocity. Then, starting with equation 5 and writing it for the x direction only and setting acceleration equal to zero, we get a second equation relating position, velocity, and time. If you look closely at equation 6, you'll notice that it would give us the same result as equation 4. By convention, the y direction is oriented vertically away from the Earth's surface, and acceleration in this direction is negative g. If we plug this into the kinematic equations for constant acceleration shown on the right, we can obtain equations that apply specifically to projectile motion in the y direction. So starting with equation 4, rewrite the equation for the y direction only and set acceleration equal to negative g. We get an expression relating velocity and time. And then starting with equation 5, rewriting it in the y direction and setting acceleration equal to negative g, we get a second equation relating position, velocity, and time. Unlike before, equation 6 will give us additional information this time. So setting acceleration equal to negative g, we get an expression relating position and velocity. Here's a summary of the equations we just derived. Note that these equations can be easily rederived from the kinematic equations for constant acceleration by plugging in the appropriate value for acceleration in the x or y direction. Let's do an example. We're told that a ball, we'll call it P, is launched from the roof of a building that is 100 meters tall. Its initial velocity is 50 meters per second at an angle 45 degrees above the horizontal. We're asked to find the distance the ball travels in the EX direction before it lands and how long it is in the air. As always, we start by drawing a picture and making sure that we have an Earth-fixed reference frame with EX and EY unit vectors. Notice that I placed the origin of my inertial reference frame E at the base of the building. I did this so all components of the position vector will be positive, both at the initial and final conditions of the problem. However, you can place the origin wherever you like. Now we'll write down what we know, but first I want to define the position vector r to be the position of p with respect to e. This will simplify the notation, but also make sure it's clear what object and reference frame we're working with. I'll do the same for velocity and acceleration. Students often ask if it's really necessary to use the subscripts, and the answer is generally yes, since we'll soon be working with more than one object and reference frame. However, if there's only one object, then defining variables like this can save a little time. Now we'll write down what we know. We know that the ball is released from the launcher at t equals 0 seconds. We also know the initial position of the ball. And we know the initial velocity is 50 cosine 45 degrees EX plus 50 sine 45 degrees EY. We know that the initial acceleration is negative g EY. We don't know when the ball will land, but we need to find that. We know the final position in the EY direction, but not the EX direction, which we need to find. There's no acceleration in the x direction, so the velocity in the EX direction is the same as the initial velocity in that direction, but we don't know the final velocity in the y direction. Finally, we know that acceleration in the EX direction is 0, while acceleration in the EY direction is negative g. To find the time that the ball remains in the air, choose an equation based on the information we have and the information we need. Again, we'll work in the EY direction and use the circled equation since we have the initial and final positions in the EY direction as well as the initial velocity. Rewriting the equation with the appropriate subscripts and plugging in values and rearranging, we end up with a quadratic equation. Hopefully you remember the quadratic formula. If not, it's shown here. And if you apply the quadratic formula, you should find that t is 9.4 seconds. Finally, we can find the distance traveled in the EX direction. Once again, we'll use the equation circled because we know the initial position and velocity, and now we have time. So write the equation, plug in values, and do the calculation. We find that x1 is 332 meters. For projectile motion problems, students sometimes get confused by the initial and final conditions. In particular, they assume that the initial and final velocities must both be 0 since the projectile starts from rest and ends at rest when it hits the ground. While it's true that projectiles must initially be accelerated to get them into the air and the ground brings them to a quick stop, we are just interested in the motion between the initial and final accelerations in this case, from the moment the projectile leaves the launcher to the moment just before it hits the ground. This is a bit counterintuitive, but remember that we're working with continuous kinematic equations, and so the initial and final conditions must also conform with those continuous equations.